Let's talk about Elasticsearch architecture and how it actually scales itself out to run on an entire cluster of computers that can scale up as needed. Elasticsearch's main scaling trick is that an index is split into what we call shards, and every shard is basically a self-contained instance of Lucene in and of itself. The idea is that if you have a cluster of computers, you can spread these shards out across multiple different machines. As you need more capacity, you can just throw more machines into your cluster and add more shards to that entire index so that it can spread that load out more efficiently. So the way it works is once you actually talk to a given server on your cluster for Elasticsearch, it figures out what document you're actually interested in. It can hash that to a particular shard ID. So we have some mathematical function that can very quickly figure out which shard owns the given document, and it can redirect you to the appropriate shard on your cluster very quickly. So that's the basic idea. We just distribute our index among very many different shards, and a different shard can live on different computers within your cluster. Let's talk about the concept of primary and replica shards. This is how Elasticsearch maintains resiliency to failure. One big problem that you have when you have a cluster of computers is that those computers can fail sometimes, and you need to deal with that. So let's look at this example. We have an index that has 2 primary shards and 2 replicas. So in this example, we're going to have 3 nodes. And a node is basically an installation of Elasticsearch. Usually you'll see one node installed per physical server in your cluster, and you can actually do more than one node per server if you want, but it would be a little bit weird to do that. But the design is such that if any given node in your cluster goes down, you won't even see it as an end user. You can handle that failure. So let's take a look at what's going on here. In this example, I have 2 primary shards. That means that those are basically the primary copies of my index data. And that's where write requests are going to be routed to initially. That data will then be replicated to the replica shards, which can also handle read requests whenever we want to. So let's take a look at how this is set up. Elasticsearch figured this all out for you automatically. It's a big part of what Elasticsearch provides on top of Lucene. It manages this redundancy for you. So if I say I want an index with 2 primaries and 2 replicas, it's going to set things up like this if you gave it 3 different nodes. So let's look at an example of failover here. Let's say that node 1 were to fail for some reason. It had a disk failure or the power supply burned out or something like that. So in this case, we're going to lose primary shard 1 and replica shard 0. But it's not a big deal because we have a replica of shard 1 sitting on node 2 and another replica sitting on node 3. So what would happen if node 1 just suddenly went away? Elasticsearch would figure that out, and it would elect one of the replica nodes on 2 or 3 to be the new primary node. And since we have those replicas sitting there, everything will be fine. We can just keep on accepting new data, and we can keep on servicing read requests because we're now down to 1 primary and 1 replica, and that should be able to get us by until we can restore that capacity that we lost with node number 1. Similarly, let's say node number 3 goes away. In that example, we lost our primary node 0, but it's okay because we had a replica sitting on node 1 and node 2, and Elasticsearch can just basically promote one of those replicas to be the new primary. And it can get by until we can restore the capacity that we lost, so you can see using a scheme like this, we have a very fault-tolerant system. In fact, we could lose multiple nodes. Node 2 is just serving replica nodes at this point, so we could in fact even tolerate node 1 and node 2 going away at the same time, in which case we'd be left with a primary on node 3 for both of the shards that we care about. So it's pretty clever how that all works. Now there are some things to note here. First of all, it's a good idea to have an odd number of nodes for this sort of resiliency that we're talking about. Also, the idea is that you would just round robin your request as an application among all the different nodes in your cluster. It would spread out the load to that initial traffic. Maybe your application manages distributing those requests across different nodes, or maybe you have some sort of load balancer device that does that for you. Let's talk a little bit more about what exactly happens when you write new data or read data from your cluster. So let's say you're indexing a new document into Elasticsearch that's going to be a write request. Now when you do that, whatever node you talk to will say, okay, here's where the primary shard lives for this document that you're trying to index. I'm going to redirect you to where that primary shard lives. So you'll go write that data, index it into the primary shard wherever that node lives on, and then that will automatically get replicated to any replicas for that shard. Now when you read, that's a little bit quicker. They just route it to the primary shard or to any replica of that shard. So that can spread out the load of reads even more efficiently. So the more replicas you have, you're actually increasing your read capacity for the entire cluster. It's only the write capacity that's going to be bottlenecked by the number of primary shards that you have. An unfortunate thing is that you cannot change the number of primary shards in your cluster later on. You need to define that right when you're creating your index up front, and here, by the way, is what that syntax for that would look like through a REST request. We would specify a put verb on our REST request with the index name, followed by a setting structure and JSON that defines the number of primary shards and the number of replicas. Now, this isn't as bad as it sounds because a lot of applications of Elasticsearch are very read-heavy. You know, if you're actually powering a search index on a big website like Wikipedia, you're going to get a lot more read requests from the world than you're going to have indexes for new documents. So it's not quite as bad as it sounds. For a lot of applications, oftentimes you can just add more replicas to your cluster later on to add more read capacity. It's adding more write capacity that gets a little bit hairy. It's not the end of the world, though, if you do need to add more write capacity. You can always re-index your data into a new index and copy it over if you need to. But you do want to plan ahead and make sure that you have enough primary shards up front to handle any growth that you might reasonably expect in the near future. We'll talk about how to plan for that more toward the end of the course. By the way, just as a refresher, let's also talk about what actually goes on with this particular put request for it. We're defining the number of shards. So in this example, we're saying we want 3 primary shards and 1 replica. How many shards do we actually end up with here? Well, the answer is actually 6. So we're saying that we want 3 primary shards and 1 replica of each of those primary shards. So you see how that adds up. We have 3 primaries times 1 replica per primary, which is 3 total replicas, plus the 3 original primaries, which gives us 6. If we had 2 replicas, we would end up with 9 total shards, right? 3 primaries and then a total of 6 replicas to give us 2 replica shards for each primary shard. So that's how that math works out. It can be a little bit confusing sometimes, but that's the idea. Anyway, that's the general idea of how Elasticsearch scales and how its architecture works. The important concepts here are primary and replica shards, and how Elasticsearch will automatically distribute those shards across different nodes that live on different servers in your cluster to provide resiliency against failure of any given node. It's pretty cool stuff.